Okay.
Okay, so before we start, let me just say a few things about how we're going to have this seminar. So if you have any questions, feel free to use the raise hand option in the participant window. So if you go to the you go to the participants, and then you can choose to raise your hand, and then we will basically go through. We will have some break times for the questions, and then we will go through the hands raised one by one. And that's pretty much the thing that we have. And also there's an option of having claps and likes. So if you want to just give your virtual clap to Tom, that would be great too.
Sort of jazz hands.
Yeah. And also, it would be great if some of you are willing to just to share a video, because I know it's hard to give a talk as a speaker that is just facing names and without videos. Great. And all right, so now let me just introduce Tom. So today we're very lucky to have Professor Tom Ditterich to give a AI seminar, and Tom is a Professor Emeritus in the School of Electrical Engineering and Computer Science at Oregon State University, where he joined the faculty in 1985. And Tom is one of the pioneers of the field of machine learning and has authored more than 190 refereed publications and 2 books. And his research is motivated by very challenging real-world problems with a special focus on robust artificial intelligence and sustainable development. And he's best known for his work on ensemble methods in machine learning, including the development of error-correcting output coding. And he's also invented MAXQ method for hierarchical reinforcement learning. And he has a long record of service for the AI and machine learning community, including being the president of AAAI, president of IMLS, and the executive editor of machine learning. And he currently serves as one of the moderators of the arXiv machine learning category. So, and also he's active on Twitter, and he's been kind of the opinion leader on some of the recent discussions about AI and machine learning, and how should we move forward. So with that, let's welcome Tom for the very interesting and exciting talk.
Okay, well, thank you very much. It's nice to have this chance to talk to you all. I'm sorry I can't be at CMU in person, but I guess none of you are there either. So it's a very carbon neutral way of visiting the campus. So this work really is the fruit of about 10 years of research in close collaboration with my colleagues Alan Fern and Wang-Keen Wang in computer science, and Debashis Mondal and Sharmadeep Bhattacharya in the statistics department here at Oregon State. And the work is there have been several graduate students that have contributed. In particular, you'll see work by Andrew Emmett, who's finishing up a master's degree with me, Shubhamoy Das, who's currently postdoc, finished a PhD with Wang-Keen, Rishit Garapalli, who's one of our current students, jointly supervised by Alan and me, Zoe Josepatis, who just finished a master's, Si Liu, who is just about to finish her PhD in statistics with Debashis Mondal and me, and Mohammed Amran Siddiqui, who was one of Alan's students and graduated last year, and Tadessa Zamichael, who just finished his defense last week. So I'll try to show you some of their faces as we go through the talk. Okay. So the outline is going to be kind of a tour through several different topics. I want to start by defining the problem of anomaly detection or novelty detection. Because I think it's been, compared to supervised learning and unsupervised learning, it's been less studied. Although certainly interest in it has really picked up in the last few years, because primarily I think because of the interest in robust AI doing computer vision in open worlds, things like this. So first I'll talk about a benchmarking study that we did because it turns out in the KDD literature, there's a longer history of anomaly detection algorithms, and there are quite a few algorithms that have been published there. And we wanted to understand when we first entered this area, well, what is the state of the art? Then I'll describe a pack learning theory of anomaly detection that was really developed by Alan Fern. And then some work by Amran Siddiqui on incorporating feedback during the anomaly detection process, which is probably the most exciting practical discovery that we've made in doing our work. And then I want to talk about two applications. One involves a big weather station network in Africa, and the other is the method for setting thresholds for open category detection. Okay, so what do we mean by anomaly detection? We assume we're going to be working with data that are in the form of feature vectors in d-dimensional real space, and that our data consists of a mixture of what we'll call the nominal points, which are the non-anomalies, the normal points, and the anomaly points. And sometimes I'll talk about the anomalies as being the aliens when we're thinking about open category detection, where they belong to new classes that were not seen in the training data. They're the alien classes. And an anomaly is not just a statistical outlier. In fact, it may not be a statistical outlier. The key thing is that these anomaly points are being generated by some process that's different than the process that's generating the nominal points. So in financial transactions, the anomalies may be generated by fraudulent, criminals engaging in fraud. In diagnosing machine failures, these could be, broken machines or broken sensors in a weather network. So we'll denote by A of X the anomaly score that's computed by some anomaly detection algorithm, with the idea that larger scores generally mean things are more anomalous. And we may have many different kinds of goals. One might be basically kind of data cleaning. Given a set of data points, we want to maybe find all the anomalies in that training data, or maybe that training data is also, in some sense, our operational data, and we want to find the fraudulent or transactions in transaction data. Another thing we might want to know is whether a new query point that was not in our training data is a nominal point or an anomaly point. So it's a kind of a classification type of problem, except that we don't have any training data for the anomalies. So there are three settings, actually. The first one is supervised anomaly detection, where we do have training data. The second one is where the training data are clean, so they're not contaminated with any anomalies, but our test data is going to contain anomalies, and so we want to detect those. And the third is the sort of unsupervised case where both our training and our test data have anomalies in them, and we want to deal with that fact in one way or another. So the supervised case, I think, is the least interesting because in most applications of anomaly detection, the anomalies are very rare. And so even if you have labeled anomaly data, it represents such a tiny fraction of your training data that supervised learning really can't work with it. The class imbalance is too severe. For instance, we might have anomaly rates of 1 in 10,000 or 1 in 100,000. And so that's a very hard case for supervised learning. So we'll focus mostly on the unsupervised case, but we'll also look at the clean case a little bit. So another important question about any application of anomaly detection is whether we can assume that the anomalies are coming from a well-defined probability distribution. And I call this the WDAD, or the WDAD assumption, which is, so we might have a case where, say, the anomalies are from repeated instances of known machine failures, in which case we might be willing to assume that the machines are not adversarial, and so this is some well-defined distribution. And it's just so sparse that we can't model it well, so we need to treat it as anomalies. But in most applications, it's very risky to make this well-defined anomaly distribution assumption, particularly in adversarial cases, so in fraud and insider threats or cybersecurity, your adversaries are adapting to whatever the learning algorithm has discovered, and so the distribution will be shifting. Another thing is in open worlds, where there's a very diverse set of potential causes of the anomalies or processes, it's very risky to assume that we have a good sample of those. And so maybe we can't safely make this assumption. And a third kind of use case that came up in some work that I did in collaboration with Kiri Wagstaff at JPL, where she was working with scientists on the Mars Science Observatory, or Mars Science Lab, I can't remember the correct name, but they were looking at data from spectrophotometers, I think, for them, an anomaly was just a scientifically interesting point that was not typical of the points they were getting. And so their goal was to find those interesting points. But once we'd shown them an interesting point, it was no longer interesting to them. They wanted to see something new. And so the notion of what was interesting was changing over time. Okay, so what are the strategies? Roughly speaking, there are two main strategies. And they depend on what is the relative frequency or fraction of the anomalies. So we're going to denote by alpha the fraction of the training points that are anomalies. And the first case is if alpha is large, say at least 5% of the data, then maybe we can take an unsupervised learning approach and fit a two-component mixture model, where one component will be for the nominals and the other will be for the anomalies. And if we have a rough idea how big alpha is, we can even a priori say, well, we want one mixture component that covers 5% of the data and another one that covers 95% of the data. Of course, this requires that we make the WDAD assumption because we're modeling the anomalies as having a distribution. And of course, it requires that the mixture components be identifiable and so on. The second case is where alpha is very small, and as I mentioned, it can be very small. And in this case, we typically approach anomaly detection by treating it as outlier detection. So we're hoping that the anomalies are very distinctive from the nominal data. Then we can avoid having to make the WDAD assumption, but this will fail if the anomalies are not outliers, and particularly in adversarial cases where your adversaries are trying to look like they're normal. That can be quite difficult. And obviously you can only detect those if you have some, what they're sometimes called tells, something in the fraudster's behavior that is essential to carrying out the fraud that reveals the outlier nature of it. This will also fail, of course, if the nominal distribution itself has heavy tails so that it naturally produces a lot of outliers, then we're also in trouble. Okay, so as I said, the first thing we did upon entering this area was to do a benchmarking study, and this was done by my student Andrew Emmett, who in addition to being a graduate student has been a busy father. And he noticed that most of the anomaly detection papers that have been published, say in the KDD literature, only were evaluating on a few data sets. And often, because this was work done in a corporate setting, those were proprietary data sets or privacy protected in some way. And so the only public data sets people tended to use were very easy ones like the KDD cup from 1999 that turns out to be a very simple problem. And so we wanted to produce a large collection of benchmark anomaly benchmark data sets. And we had a paper at this, the ODD workshop at KDD back in 2013. And then there's a paper on arXiv that Andrew is revising right now. So the methodology was to go to the UC Irvine repository of data sets and select all the data sets that satisfied certain properties. We wanted real valued or at least ordinal valued features. We needed enough data basically. And then what we did was most of these were classification problems, so we would choose one or more of the classes to be the anomaly classes and the rest to be the nominal classes. And usually we looked at the actual domain and the application, because sometimes the anomalies made sense as anomalies. For example, in the space shuttle data set, several of the classes really are anomalous classes. And then we wanted to manipulate 4 properties that we thought would have some bearing on the difficulty of the problem. One is obviously the relative frequency of the anomalies, so our parameter alpha. Another one was we could fit a supervised learner to the data and then ask how hard is each individual point to separate from the nominals. So we could vary that. We could vary the amount of irrelevant dimensions in the data by just adding irrelevant features. And then we tried to manipulate, this was the one that was hardest to manipulate, the clustering of the data, right? Because many anomaly detection algorithms are basically doing some form of density estimation or some measure of distance to nearest neighbors. And if the anomalies themselves tend to form clusters, that defeats those kinds of algorithms. So we wanted to manipulate clusteredness. So we created 20 replicates of each configuration of these 4 variables that we're manipulating, and the 19 data sets, which we call the mother data sets, because they give birth to all these children. And we end up with more than 25,000 benchmark data sets. And then we're going to compare several algorithms, and we chose 2 metrics. One is the area under the ROC curve. So this is essentially a measure of how well the anomaly detection algorithm can rank, give a higher anomaly score to anomalies than it does to nominal points. And we're going to do some linear regression and analysis of variance. And so we transformed this to its log odds form for that purpose. And we also looked at average precision, which of course is equivalent to the area under the precision recall curve or to the average of the precisions computed at each of the ranked anomaly points. And again, we transformed this as being the log lift. So we took the average precision divided by the expected value from random ranking, and that gives us our lift, and then we log transformed that. So we wanted to compare, do a good survey of kind of the state of the art. So we looked at 4 general families of anomaly detection algorithms. The first family is density-based methods. So we try to fit a probability density estimator to the data. And I like very much the work by Kim and Scott. So Clayton Scott has done quite a lot of interesting work in this area. And they have a very nice algorithm called robust kernel density estimation, which is a bit like a support vector machine type of approach, but using a sort of Huberized type loss. And then in our group, we had been fitting ensembles of Gaussian mixture models with different numbers of mixture components and having some success with that. Then there are probably the most famous algorithms in machine learning are the one-class support vector machine. They came out of Sholkov's group back in 1999, and the support vector data description from Tax and Doyne. And both of these attempt to basically find a level set or a quantile of the probability density. So it's a decision boundary that contains, say, 1 minus alpha of the data points. And the thought then is you can treat the points that are outside the boundary as being the points you're predicting to, or you're treating as the anomalies. Then, of course, I'd say another very famous method is the local outlier factor, just using the distance to the k nearest neighbors, but normalizing that by the distance of those points to their k nearest neighbors gives you the LOF method. And there's something called ABOD that uses the angle if you're sitting on a data point, you can sort of look at the rest of the data and ask how big is the angle that rest of the data has. If you're an anomaly far away from the rest of the data, that's going to be a small angle. If you're buried in the middle of the data, that's going to be like 180 degrees type angle. So it's an interesting method that is less dependent on the distance metric. And then there are these projection-based methods, the isolation forest, which I'll describe in a moment, and LODA, which is basically generates sparse low-dimensional projections of the data and fits a one-dimensional histogram estimator of the density and builds an ensemble of those and uses those density estimates for anomaly detection. Well, it turns out the algorithm that we found performed the best was something called the isolation forest, which was developed by Liu and Ting from Monash University and Jihua Zhou from his famous lab at Nanjing. It works as follows. We're going to construct a forest of isolation trees, and each isolation tree is a random binary space partitioning tree. So we construct it by choosing an attribute J at random from the data, and then looking at the minimum and maximum values of the J attribute, and choosing a threshold theta 1 uniformly from this range, and then splitting the data, and then doing that recursively. And the idea is we want to keep splitting until every data point is in its own leaf, which will be possible unless there are data points that are identical, in which case, obviously, they'll be isolated together. And what we're interested in is the depth of the point. It's so-called isolation depth. So this point xi has depth 3 because it had to go through 3 splits before it was isolated. And the intuition is that that points that are outliers will be much easier to separate, to isolate from the nominals than points that are deep inliers that are surrounded. So an outlier, maybe 1 or 2 splits might be enough to separate it. But an inlier, you may have to split many times to separate it from all of its neighbors. And so that's the intuition. It's a very sort of non-parametric intuition. And we build a forest, say, of 100 of these trees, and then calculate the average isolation depth of a point. And Liu, Ting, and Zhou show how to normalize this in terms of the sort of expected isolation depth for random binary trees. And they give us a score between 0 and 1, where things that have a typical depth will have a score of 0.5, and anomalies will typically have scores higher than that. So it's a nice normalization and suggests setting your anomaly threshold somewhere 0.51, 0.52, something like that. Okay, well, we wanted to understand the relative importance of the various factors in explaining the observed AUC or log lift. And so we did an analysis of variance based on this linear model, that the metric was a linear combination of the relative frequency, the point difficulty, the degree of clusteredness, the level of irrelevant features, and for each of these we defined various fixed levels. The mother set, which is really the domain the data comes from, and finally the choice of anomaly detection algorithm. As we were, one lesson we find in machine learning very often is the algorithm is not the most important factor in the performance, in the accuracy that's attainable on a data set. So we wanted to assess the algorithm effect while in some sense controlling for all these other sources of variation. And so if we look at that and we ask, well, what is the change in explained variance that's due to each of these components? It turns out that for AUC, it's the choice of the data set that explains the most variability. And for log lift, it's the relative frequency that's most important, and the data set is second most important. So the top 2 most important things are the data set and the relative frequency. And the choice of algorithm is only the 3rd most important factor. And so this, of course, makes sense. But we were surprised that the difficulty of the points, or the amount of irrelevant features, or the clusteredness, those made relatively little difference, especially for AUC. For lift, the clustering did have a bigger impact. So keeping all that in mind, that the choice of algorithm is the 3rd most important thing, which algorithms did well? Well, as I sort of hinted, the isolation forest was our best scoring algorithm. And we normalized this relative to a sort of a control baseline data set that had a sort of standard setting of all the different things we were varying. And so that we could interpret for data sets that were harder or easier, that kind of controls for that. And what we see is that the isolation forest scores the best on both metrics, and then there's maybe a 4 or 5 way tie for second place. And then what was shocking was that the one-class support vector machine and especially support vector data description performed really badly on our problem in our experiments. Now, of course, maybe in different hands, but the trouble is, of course, there are some parameters you have to tune with these methods. You have to choose the kernel width, and you have to choose the quantile that you're going to try to measure. But we suspect that probably what's going on here is that these methods, we're scoring them basically on how well they rank points, but they're not trained on a ranking metric. They're really trained to learn a decision boundary, and so our hypothesis is that the resulting decision function that they learn is not particularly good for ranking, even though it's very good as a decision function itself. So there's a recent paper from NeurIPS 2 years ago that by Menon and Bob Williamson, and Bob was one of the co-authors of the one-class SVM paper, that suggests a way to improve this. And so I have an undergraduate who's trying to get that to work right now. So maybe we can get rid of this problem with an improved version of one-class SVM. Okay, so the advantages the isolation forest seems to have, if you dig down, is that it's more robust to irrelevant features for both area under the curve and lift. Okay, well, I better move along here. So the next topic I want to talk about is a PAC theory of rare pattern anomaly detection. And this is work by Amran Siddiqui, who's shown here, and Alan Fern. So here we're interested in the sample complexity of anomaly detection. And if you look at the literature for density estimation methods, such as the kernel density estimation approach, the sample complexity is known to be exponential in the dimension of the space. And these are minimax results, so they're matching lower bounds. So that's very depressing. For the quantile methods, on the other hand, there's polynomial sample complexity, so that's exciting. And we noticed experimentally that many of these anomaly detection algorithms learn very quickly. So they typically have converged to their best performance after maybe 500 and at most 2,000 examples. So it seems experimentally that the sample complexity is low. How could we explain that? Well, Alan came up with the following theory, and the idea is, this is very much in the style of concept learning for PAC. We're going to define a pattern to be an indicator function over some measurable region of the input space that just maps that region points to 0, 1. So an example might be half planes or axis parallel hyperrectangles, or ellipsoidal volumes if we're using Gaussians. And then we'll define a pattern space to be a set of these patterns. And then we'll say that a pattern is rare for a particular data set if it has low probability. So to do that, technically we need to do this as a ratio of two measures. So we define some baseline measure, mu, that's going to be a fixed measure over the space. Maybe it's uniform in the unit hypercube, or it's a Gaussian, or something like this. And so then mu of h is going to be the measure of a particular pattern h under mu. And then we'll let p be the nominal probability density defined on RD. And p of h will be the probability mass of that pattern. And so then the pattern we'll say is tau rare if the ratio of p divided by mu is less than or equal to tau. And we'll call that ratio f. So a pattern is rare if it has small measure, small probability. And otherwise it will be said to be a common pattern, so it will be tau common. Okay, so now we come to saying, well, what does it mean for a point to be rare versus common? And we'll say a point is going to be tau rare if there exists a tau rare pattern for which that captures that point. So the picture you should have in your mind is the way we're going to do anomaly detection is to surround the data with these patterns that are rare. And we can have them overlap overlapping in various ways, but they should all cover very few of the nominal patterns. And then if an anomaly falls into one of those rare patterns, then we'll declare it to be an anomaly. And so our ideal algorithm would be one that outputs all tau rare points and doesn't output any tau common points when it's given a set of points to score. So we'll say an algorithm then is pack Arpad if for given pattern space and measure and parameters tau, epsilon, and delta, for any probability density p over the nominals, and for any tau, the algorithm draws a sample that is polynomial in size in the relevant parameters, and with probability 1 minus delta, it detects all of the tau rare points, and it rejects all of the tau plus epsilon common points. So we're giving it an approximation margin here. For the points that are between tau and tau plus epsilon, it can treat those points arbitrarily. And it needs to do this in polynomial time and samples. So the simple algorithm for a finite pattern space is to draw a sample of a certain size that we'll describe in a moment, and then just empirically estimate the probability of each pattern, normalize those by our underlying measure, and then simply report out all the query points that are in rare patterns. And then we can prove that rare pattern detect has a polynomial sample complexity. So you get results that are very familiar, that we have a dependency of 1 over epsilon squared times the log of the size of the hypothesis space, and then a log term in 1 over delta, which is the confidence level. And if we are in an infinite space with a finite VC dimension, then we get a bound like this that has similar linear dependency on the VC dimension with a 1 over epsilon squared log 1 over epsilon squared dependency. Okay, so that's cool, and it models the kinds of things that we see in these algorithms. So for axis-aligned hyperrectangles, these are like the leaves of an isolation forest. For Loda's random histograms, the stripes correspond to bins of those histograms in random projections. For our Gaussian mixture models, those are ellipsoids, ellipsoids. So we decided to try to create a theoretically justified version of isolation forest that we call isolation Arpad. And the idea is we divide our training data in half, and we use half the data to grow an isolation tree down to some fixed depth, depth k. And then we say each leaf defines a pattern, and we use the Lebesgue measure as our underlying measure, so just the volume of these hyper rectangles. And so we estimate f hat using the second half of the sample, and then we score query points by just taking the union of all these patterns. And here are some learning curves where we have the log of the sample size on the x-axis, and the vertical axis is the AUC. Unfortunately, I realize these are not on the same scale. So here's isolation forest grown to different depths, and then this isolation Arpad grown to those same depths. And we see that the range here is from basically 0.8 to 0.95, so that would be just in this range here. But the qualitative shape is that these things converge in, say, 1,000 samples, and that's roughly the same, and the performance at convergence is roughly the same. This pattern min is much worse at very low sample sizes. But if we look at another one, and here the vertical axes are the same, this is for the Shuttle data set, we see that in this case, actually, the theoretically justified algorithm actually is performing better than the isolation forest. So it varies, and you can look at the paper and see there's quite a lot of variability. So we think that this pack-Arpad theory is capturing the qualitative behavior of algorithms such as the isolation forest, and it's certainly easy to design practical Arpad algorithms. The theory could be improved to use sample-dependent pattern spaces rather than spaces that are fixed a priori in the way that it has been done for supervised learning. Okay, well, now I want to talk about what's probably the most exciting finding, which is incorporating analyst feedback. Hello? So in a lot of problems in fraud detection or cybersecurity, the workflow is really something like the following. You pull in a bunch of data, say, transactions for a day or a week. You apply anomaly detection and get scores for these. You rank them and show the best candidate, the most suspicious point, to an analyst. And the analyst has to decide, is this a false alarm or is this a true alarm? And so I need to, launch an investigation of this fraudulent case, this potentially fraudulent case. Well, since an analyst is looking at these points, we should use the feedback from the analyst to update the anomaly detector and then re-rank the points and show then the next best candidate and so on. So we can incorporate this analyst feedback. And we had a first method that we called active anomaly detection that was by Shubhamoy Das as part of his PhD thesis. And then Amran Siddiqui developed an improved method that is called Generalized Linear Anomaly Detector, or GLAD. It was published 2 years ago at KDD. And so these are the kinds of results that we get. On the horizontal axis here is the number of times we go through this analyst iteration. And these are simulated. We're using a supervised learning, a supervised learner as our analyst. And so what we see is that the dotted line down here is if we just apply the anomaly detector, rank the points, and then just present them to the analyst in order with no feedback. And we see that out of 100 candidates, maybe we only detect 22, I don't know, that were true anomalies. Now with the active anomaly detection, Shubhamoy's algorithm, we get about 52 or something. And with this active anomaly detection, more like 70. So you can see we're getting a huge improvement in the precision of the anomaly detection by being able to take analyst feedback. And this is confirmed in several different of our benchmark data sets. So of course we were very excited about this, but I was also a little nervous because these are benchmark data sets that were originally classification problems. So that means there really is a decision boundary that can reasonably separate the classes, right? Otherwise, it wouldn't have been formulated as a supervised learning problem to begin with. So maybe this is not surprising. But we've also been involved in a DARPA program called Transparent Computing, where the goal was to find advanced persistent threats in networks. And so there was a red team that there was a small network we were working with, and the red team would inject attacks into these things, and then we needed to find them. And so we, of course, hand engineered a bunch of features. We're applying isolation forest, and what I'm plotting on this now, the vertical axis is like the horizontal axis over here. It's the number of candidates we have to present to the analyst before we detect the first true anomaly. And using the baseline method, just using our initial anomaly ranks, it takes 43 iterations on host number 1 to hit before we get one positive hit, compared to 3 if we use the analyst feedback. With host 2, 60 something versus 10, and host 3, 40 something versus 20 something. So again, dramatic improvements in the ability to quickly detect true anomalies. And so I'm very excited about this because obviously in this case, there was a red team trying to elude us, and we still saw this effect. One concern we still have about this is it losing certain modes, right? Because it could be that essentially what's happening is it detects a particular kind of attack and then just exploits that attack. It's not really shown here, but in this kind of curve, it detects one type of anomaly and then just keeps presenting more and more of that same type to the analyst. And the question is, was it missing other types? And I don't have data on that, but that's something that Wenqing Wang has been looking at. When he was a PhD student at Carnegie Mellon, he worked on this problem that's also known as rare category discovery, which is again in an active learning framework where your goal is to discover all the different rare cases, different categories or clusters as quickly as you can. And so he's trying to extend that to this setting. Okay, so one word on the method that we're using. which is that we transform the isolation forest into a gigantic linear model. Basically, if you imagine introducing a Boolean feature or an indicator variable for every node in every one of those trees, then if a query, as it's being processed, visits that node, it turns on that feature. Okay, and then imagine assigning a weight to each feature that is a weight of 1. And then we can we drop the query through 100 trees, and that turns on a bunch of those indicator nodes. We sum up all of those, and we get the total isolation depth that's equivalent to the total isolation depth of that query point going through all of those trees. So we've converted the isolation forest into a linear model, and then we use online mirror descent, right, which is these accelerated linear methods to adjust the weights, to reduce the weights, the anomalies, the isolation depths of the anomalies, and increase the depths of the nominals. And that's all we're doing. And I'm just super impressed by how quickly these online convex optimization algorithms are able to adapt to the data. It's very cool. Okay, well, in the remaining couple of minutes, I want to describe 2 applications. The first one is to the Tommo Project, which is an effort by some colleagues of mine, particularly John Selker, who's a hydrologist, and Nick van de Giesen, who's at Delft University, Technical University of Delft. They have created a nonprofit company called Tommo, whose goal is to deploy and operate a network of 20,000 weather stations in all of sub-Saharan Africa. And this was motivated by the observation that this map at the top shows weather stations that regularly report data to the World Meteorological Organization, which is the UN specialized agency for weather. And we see that in most of South America and most of Africa has very poor weather infrastructure. And what that poor infrastructure means is they also have relatively bad weather forecasts. They have no crop insurance industry because insurance companies aren't willing to write insurance without good data. And indirectly, this leads to poor agricultural productivity because most of the agriculture in Africa is rain-fed, it's not irrigated. And so farmers adopt very conservative strategies in planting their plants, say planting them very far apart. And there's lots of evidence that if we could provide crop insurance, that would allow farmers to be more aggressive in their planting because they don't face the same downside risk and could improve agricultural productivity. My role on the project is automated data quality control. So I want to detect broken sensors using anomaly detection. One of my slogans is that the Internet of Things is the Internet of broken things. And so we have developed a strategy, and I'm kind of running out of time here, so I can't go into a lot of detail, but the basic idea is to divide up take all of this weather data. We have, right now we have about 550 weather stations that have been deployed. Each of them has 7 instruments on it, or sensors, and those are reporting every 5 minutes. And so we can think of it as having a huge joint distribution in time and space and trying to find anomalies in that spatial temporal distribution. But more practically, we need to do it more or less in real time. So we divide up this data into a bunch of database views, and we fit anomaly detectors to those individual views. And then we combine the anomaly scores by the different views into a big probabilistic model in which the observations are the anomaly scores of different sensor combinations. So for instance, if we consider temperature and relative humidity, those 2 sensors, we can have a sort of time series view of the weather, of the temperature, a time series view of the humidity, and then a joint view of just the temperature and humidity at one particular moment in time, because they are highly anti-correlated. As the temperature goes up, the humidity goes down, and vice versa. And so then we introduce these variables, which are the variables that correspond to the state of the sensor, working or broken, at each time step. And so if we want to diagnose whether sensor 1 at time 2 is working or broken, here's the evidence that directly bears on that. And of course, there's also indirect from its Markov blanket. We pick up the same sensor at different time steps and so on. And so we can turn this into a problem of probabilistic inference to find the assignment of states to the sensors that maximizes the likelihood of the anomaly scores. And so Tadessa Zamichael, who's shown here, just defended his thesis last week, evaluating this strategy on data from Oklahoma, which has one of the best weather networks in the United States. And I can't go into all the details, but we took 4 weather stations and we inserted synthetic faults, realistic synthetic faults, into the data, and then we measured how well we were able to what our precision at a set recall level is. So recall in this case is detecting failed sensors, and precision then is, you know, how many of our detections were false alarms versus true alarms. And what we see is that using this joint probabilistic approach is it has higher precision, 6 to say 12 percentage points higher than using a simpler method that just looks at each individual sensor for just local things, which is basically the state of the art right now. And here's what, for matching levels of recall, here's the precision compared to the baseline. And you can see that we're able to go from, say, 0.15 to 0.3. You say 0.3 precision, that sounds awful, and it is. But one of the key things about broken sensors is typically once they break, they stay broken. And so we can aggregate these anomaly scores over long periods of time and get the precision to be much higher. So this is the precision for a single 5-minute interval. So it's not as bad as it looks. Okay, so we're in the process of deploying this onto the Tommo network right now and integrating it with a network manager dashboard that's used by a person whose job is to just monitor the network and assign trouble tickets to field technicians to go visit the stations that are broken. And I don't know if I have time to describe this, but I'll just introduce you to my brilliant student, Si Liu, who's just graduating this quarter. And we've been looking at the question of using anomaly detection for rejection and particularly for detecting novel categories in supervised learning. So the idea is, given some training data, we fit an anomaly detector and a classifier to that data. And then given a new query, we first calculate its anomaly score. And if that score is too high, then we reject that data point and say either this looks very different from our training data, so we're just likely to get it wrong, or we think this even belongs to a new category that we didn't see in training. And so the hope is that then that we can give a guarantee, or the question was, can we give a theoretical guarantee that that if we do classify something, that we will get it right with some probability. That is to say, can we detect with high confidence all of the things that we should be rejecting? And so I can't go through all the details, unfortunately, but the basic thing we get is a theoretical guarantee that with probability 1 minus delta, our alien detection rate for detecting these anomalies will be at least 1 minus Q plus epsilon. So there's been a lot of work in the past on giving anomaly guarantees that give a guarantee on the number of false alarms that you'll give. And to do that, you need to estimate the tails of the nominal distribution. And of course, the nominal distribution, you have a lot of training data for that. And so that's a pretty easy problem. But in this case, what we're trying to do is estimate the tails of the anomaly distribution. And we have less data for that. And we have no labeled data at all. And so the strategy involves assuming that we have access to an unlabeled collection of mixture data. So it's kind of related to the what's sometimes called the positive unlabeled supervised learning task, that I have training data that consists of positive examples and then no negative examples, but I have a mixture of unlabeled data that contains both positive and negative examples. So the situation is similar. So we get basically 1 over epsilon dependence. There's a pattern here, and a 1 over alpha squared dependence, which is this is the anomaly, the assumed rate of aliens in our data. Okay, so I'll stop there and just review. I argue that outlier detection can be used for anomaly detection in the unsupervised or the clean case when the relative frequency of the anomalies is small. And then we had our benchmarking, which suggested that the isolation forest is the best performer, at least for featureized data, and that the quantile methods like the one-class support vector machine did not work very well. But we're trying to figure out why. And then we introduced this Arpad theory that accounts for the rapid learning of these anomaly detection methods. We showed that incorporating expert feedback can double or triple the recall or effectiveness detection of the anomaly methods. And then I showed that some applications of anomaly detection for detecting broken sensors and for providing guarantees for rejection in supervised learning. Okay, I'll stop there and answer questions.
Cool. So yeah, Christoph, do you want to go first?
Yes, can you hear me?
Yes.
Yeah.
Okay, so is there a relationship between anomaly detection and hard example mining? So if you train a classifier, you want to have a lot of hard examples because the easy examples, they don't give you much. Can anomaly detection be used for that?
That's an interesting question. I mean, we've been, of course, I never use the word deep learning in this talk. And I'd say that's the big open area is how can we do anomaly detection in the context of deep learning, right? And there have been lots of different things that people have tried there. And I would say, you know, it's still, we still have a ways to go, I think, to have a reliable method. But one of the techniques people use is the so-called Siamese networks, where you try to learn an embedding space in which distance, then, like nearest neighbor type methods can work well. And for that, they do use hard example mining to train that distance metric. But I know you're really asking if I wanted to do, say, active learning to try to get labels for data, maybe I could use anomaly detection to find the interesting cases
Right.
and get the labels for those. And that's an application I hadn't thought of, but I like it.
Yeah, but I mean, it might be that it's actually hard examples are between normal examples and anomaly, and then so it's it's still a normal thing, but it's just hard. But an anomaly might be too far out. I don't know if that's might be different categories.
Yeah, that's a good question. So I guess my answer is I don't know the exact connection, but it's a good question.
But it certainly would be very, very valuable application.
Yeah, in some sense, the NASA case that I described is like that, where the scientist wants to see the interesting cases, and then she was going to look at those cases and, in some sense, label them. And and then we had the problem that we needed to update the detector so it wouldn't find cases similar to that one. So that's another theme that's kind of traveling through here.
Yep.
Great.
Next.
So next one is Namatola.
Yeah. Thanks, Thomas. It was a very nice talk. So I have a question about the last slide, almost the last slide that you said that this problem is related to PU learning, like positive unlabeled learning, if I understand correctly. So can you elaborate on that?
Okay, well, so oops, let's see, I gotta get keyboard focus back. So the setting we assume we have is that we have our label data comes from the nominal distribution, and then we have unlabeled data that comes from this mixture distribution, and we assume that we know the proportion of the aliens that is in this, and that's a big assumption that we make. And so that's basically the same as the positive unlabeled setting, right? And I'm not sure what else to say. We then can use this. We can take advantage of the fact that what we really would like to have is the CDF of the anomaly scores, right? Because if we want to have a recall on the detect one minus Q fraction of the aliens, then we want to put a threshold. We want to choose our threshold here so that we capture 95% of the probability. But we don't have that, but we can, we know that if we know alpha, we know that FM is a mixture of the CDF of the nominals and the CDF of the aliens. So we can solve for the alien CDF, and ideally it would look like, the picture would look like this. Unfortunately, the real picture looks more like this, but you can still get some guarantees out of that.
Yeah,
So.
thank you, I got it. Yeah.
Great. Shu?
Yes, thank you. Can you hear me?
Yes.
So I have two questions. One is, can you clarify the difference among anomaly detection, out of distribution detection, open set recognition, the three concepts?
Right.
So,
yeah.
okay.
Yeah. I mean, in some sense, you can try to use anomaly detection to do OOD and open set. I think the out of distribution detection problem is actually ill-defined. I mean, if I have a distribution that has support everywhere, then there is nothing that's out of distribution. If you look at any single point, you can't tell. So it only makes sense to assume that I have some sort of limited support for my distribution, and then I have, you know, probability 0 outside of that. Then OOD makes sense. And I think a lot of the experimental protocols are kind of lame, right? Where we train on ImageNet and then use some totally different image collection method to get our OOD points. And there may be all kinds of clues in those images, just like, you know, color histograms or something that reveal that they are from a different distribution. So I'm not a big fan of the OOD setting, although obviously I've co-authored some papers with Dan Hendricks, who's a former intern of mine now at Berkeley, on the OOD problem. I'm much more interested in the open category problem. And I would say the difference there is that we assume that these categories that we've not seen during training, they are distinctive categories that are conceptually separable from the categories we know. So unlike sort of the generic anomaly detection or OOD case, where we might be looking for just distribution shift or subtle changes, these will be, one hopes, fairly marked changes. I mean, you know, they will look distinctive to a human, and I think that's also a much more practical problem in open worlds. I've had that problem in some of my application work, and it's obviously a big issue in self-driving cars too.
Cool. So here's my second question. So speaking of open set recognition, actually you can leverage the trained model for closed set classification to detect.
Right. I mean, nowadays it seems, you know, we've been doing a lot of work trying to get GANs or autoencoders to work for open set. And but we find that generally speaking, the best methods still just use the supervised classifier, even though from a theoretical point of view, that should not work, right?
Okay.
But experimentally, the supervisory signal seems to be super important to getting a good latent space representation in our experience. Are you working on that too?
Yes, I'm exploring that.
And does that match your experience too? That
I found that the GAN actually works the best in my data set. Yeah.
Oh, well, maybe you have some positive results I need to know about.
And maybe good. Tomorrow I can chat with you.
That'd be great.
Yeah. Thanks.
Yeah, that's all great. And thank you all for coming to the talk. And thank you, Tom, for giving a very exciting and wonderful talk. And yeah, last part, actually, we still have one slot remaining this afternoon. If anyone wants to sign up for a meeting with Tom, please let us know. You can email Linda to sign up for that slot. Okay, cool. Thank you, everyone.
Thank you all very much. That was fun.
Yeah.